Uh, Hello?
Yep, good afternoon.
Hi.
Sorry,
Are you Getty Minas?
getting you.
Sorry, what's your name? Who
My
are
name is
you?
Alex. Sorry, my name is
Oh,
Alex. I'm
you're
not getting
Alex.
minutes.
Hi.
Yes.
Hi, I'm Scott.
I'm sorry, you just get the email link
I
to
just
join.
got it, just a second.
So like we were
Yeah,
about to miss
I had no login to this call. Okay.
so we were about to miss the main like part of our like session. You.
Yes, just a second.
Yeah, sorry. So then let's start. Good
All
afternoon,
right, a lot of crosstalk. Okay, it's really hard to hear anything.
Hear anything what I'm saying? Oh. Crosstalk between what and what?
Yeah, so after I say anything, then I hear it like 10 seconds later. I hear myself like with a few seconds delay. All right. This is better now.
Ah, okay.
Oh, no, now I just heard it. Oh, you know what? Was that because I had some window open that has like a live feed of this? So I was trying to figure out how to get onto this call. Here we go. All right, that should be better.
Now it's fine.
Yes.
Okay, I'm sorry. So sorry for all this confusion. Like, let's start. My name is Alex. I'm the president of Quantum Information Society. And for all who have joined us, I guess you already know, but today we have a question and answer sessions with Professor Scott Aaronson. Let me say just a few words, as I usually do before like any talk. So we are coming to the end of Trinity term. We had like quite a lot of events, and I think they were quite interesting. But it's not the last event. On the next week, we'll have a journal club where my DPhil fellow, Oana Bazawan, she will tell us about two qubit gates for trap-time quantum computing. And if you're interested, last week we had a talk by Chris Monroe. He was like giving us a general overview on what is trap-time quantum computing. But if you want to learn it in more detail, so come and join us next week. And so yes, today we have a question answer session. So I can't believe it myself. Professor Scott Aaronson is a professor at University of Texas at Austin, professor of computer science. And before that, he has been taught electrical engineering and computer science or at the MIT. And in general, he's interested like in limits of quantum computers and computational complexity theory in general. But let me say like this kind of boring words, and my words are that when I got interested in quantum computing, I wanted to learn what is like P and P, what is polynomial, maybe that's not polynomial, what makes that sense. And then I have Googled the second chapter of quantum computing since Democritus. And then it was written in such a hilarious manner that I wanted to know like who is that? Why it's so funny? And I reached this Scott blog, and there was a line saying that if you want to take one thing from this blog, then it will be that quantum computers would not solve all hard search problems by just trying all possible options at once. Now the line is slightly different as far as I can tell, but still that like gave a light to me, like answered a question in my head, really annoying question. And I hope that today we'll have answers for many annoying questions in our heads. So we have got several questions from people, and I don't know, you have access to the doc. Would you like to?
I saw that there were some advanced questions, but maybe I'll let you be in charge of just deciding what question I get at a given,
Okay, of course.
All right, great. Here, just give me 1 second, please. Okay. Hey.
Okay, so I think we have several people who have sent us their questions who they're here, and I can allow them to talk if they want to. So I'm probably the first question from Maria Violaris. I mean, Maria, can you talk now? Can you listen us? Maria? Okay, I'll ask the question then by her. So,
okay, sure.
A funny one. If you had access to a universal quantum computer, what is the first thing you would do with it?
I think the first thing I would do is I would ask Gil Kalai or Leonid Levin or the other people who don't believe quantum computing could ever work. I would ask them to just give me a gigantic composite number. Just,
Okay.
You know, pick some huge primes, multiply them, send me the product. You know, I mean, for me, you know, the number one application of quantum computing has always been just disproving the people who said that quantum computing could never work, right? You know, in other words, just, you know, proving that quantum mechanics actually is true on this scale, and that nature, you know, has this computational ability at all. I mean, all of the rest of it is kind of icing on the cake for me. It's, you know, I mean, you know, I think that there are useful applications that quantum computers would have. You know, they're more specialized than a lot of people would like them to be, or sometimes pretend that they are. But, you know, I do think that quantum computers might be revolutionary for, you know, all sorts of fields that depend on quantum simulation. You know, biochemistry, material science, you know, designing new industrial chemical reactions, super high temperature superconductivity, design of solar cells. But, you know, those are not applications where I personally would have the slightest idea how to get started. You know, we would just want to make the capability available to the people who could use it. I mean, look, you know, the truth is that you know, I used to write code. You know, when I was a student, you know, I was not a terrible programmer, but, you know, then I became a theoretical computer scientist, which is one of the last refuges for people who don't, you know, who don't want to write code, right? And so, you know, what coding I do today is mostly because, you know, now because of COVID, I homeschool my 7-year-old daughter, right? And so I'm trying to teach her how to write basic programs and, you know, demonstrate different things for her in BASIC. But I mean, you know, that's like the level of my programming now. So I think that, you know, the people who are actually programming the quantum computer should be people other than me.
Okay, fair enough. But okay. Yeah. Okay.
Yeah.
The next question is kind of, I think, like what broad one. What is, in your opinion, is the current state of the field of quantum technology, and I think like of quantum computing in general?
Yeah, I mean that's an insanely broad question, but I mean, look, you know, we've all heard about, you know, Google's announcement of quantum supremacy, you know, this past fall, right? And I think that was a big milestone for the field, and it gives us, you know, a pretty good sense of where things are now on the hardware side, right? That you now have a 53 qubit programmable device, you know, that for some very, very special and useless task can apparently outperform the best that we can do with any of the classical supercomputers that currently exist on Earth. Okay, so that's tremendously exciting, but it's also very, very far from where we want to be. You know, it has no error correction, it has no fault tolerance, right? So useful quantum error correction has not yet been demonstrated, and that's regarded by almost everyone in the field as, you know, an essential precondition to making quantum computing truly scalable, right? So the first demonstration of useful error correction, by which I mean sort of error correction that achieves some net gain, you know, that keeps a logical qubit alive for longer than the underlying physical qubits are alive for, you know, even in the presence of arbitrary, you know, X errors and Z errors. I think that is a major, major milestone to look for next. You know, it might come in the next few years. I hope it does. You know, unfortunately, a lot of the experimental quantum computing work is now shut down because of COVID. But that, you know, that, right, that was the thing. Quantum supremacy was achieved, and then the whole world shut down, right? So now right, you know, at this moment, it's very hard to predict anything. You is the United States going to collapse, within the next 6 months? I'm not sure how I would bet. Okay. But, assuming that things that the world gets back on track, I think quantum error correction is a major milestone to look for next. And another thing that people will be working toward, is to do something useful with the, non-error corrected quantum computers that we can build now, the, what are called NISQ devices, the noisy intermediate scale devices of 50 or 100 or 200 qubits. So, the way that I like to describe it is that I think that we've now, with quantum supremacy, we've now entered the very, very early vacuum tube era of quantum computers, right? Where we have the noisy components, but that will hopefully be good enough to sometimes get an advantage over the best that you can get with classical computers. This was not the situation for the past 20 years that I've been in this field, where, for most of the time I've been in this field, or certainly, when I started, it was people messing around with very small numbers of qubits, with no, not even close to getting any advantage over a classical computer for anything, right? And then some people claiming to get advantages over classical computers, but not really, right? So I think it's tremendously exciting, the progress that's been made. I mean, people complain, oh yeah, it's been 35 years, so where's the, where can I buy my quantum computer on Amazon, right? So, it's true that we're not there yet. On the other hand, if you compare to where we were, say in 2000, when I started as a graduate student, it is, I think there's been a tremendous amount of progress on the experimental side. I've all of that is completely setting aside, what is the state of the field and the theory side, the algorithm side, where, of course, there's a tremendous number of things happening on a bunch of different fronts at once. But, people continue to search for new quantum algorithms. Mm-hmm. I think it's fair to say that, a lot of the most important quantum algorithms were discovered very, very early in the field. Shor's algorithm was 1994. Grover's algorithm was 1995. And a huge fraction of everything that's happened since in quantum algorithms has been variations, or extensions of those two algorithms. Okay, but there are some other ideas. There's a lot of work in the last 5 or 6 years on how do you use a quantum computer, including a very near-term one, to simulate quantum mechanics, simulate Hamiltonians in a useful way. There's been a lot of work over the last decade on quantum algorithms for machine learning. And I think the picture is very mixed. We still don't really have a killer app for quantum machine learning, where it's clear what speed up you get over a classical computer, and it's clear what it's useful for. And it's clear that, you could actually input the relevant data to the quantum computer, and get the output, measure the output efficiently. But, so that continues to be a very active research area. And then, there's lots and lots of stuff that is happening on the more theoretical side of the field, right? There was a breakthrough just earlier this year about MIP star, about, entangled provers being able to prove the halting problem, actually, that an arbitrary Turing machine halts. That was an astounding discovery. 2 years ago, we finally had the first oracle separation between BQP and the polynomial hierarchy, which is a problem I had thought about for 20 years, showing that basically even if P equaled NP, there would still be a chance that quantum computers could outperform classical ones for something. So there's lots and lots of exciting theoretical work that happens, in all sorts of directions. By its nature, that's a lot harder to predict, even than, the progress on the hardware side, which is pretty hard to predict in itself.
Okay, so probably just on the top of what you have already said, we have a question from Gediminas Pazera. I don't know if Gediminas.
Oh yeah. Okay, hi. Just give me a second. Let me try to get some more light in this room.
Yeah, of course.
Okay, hi. Yeah.
Gediminas, yes, he had a question about quantum supremacy experiment. Like.
Okay. Hi, Gediminas, and thank you for inviting me here, by the way.
Sorry for that technical difficulty.
It's all right. No problem.
Wait, can you hear me now?
Yeah, I can hear you.
Okay, so I had a question about the quantum supremacy experiment itself.
Sure.
And it seems at times that the whole experiment is taken with a grain of salt among scientists. So people seem to accept that Google have reached the quantum supremacy, but yet they still say caution.
Yeah.
So like, so being caution about what the result means. So were there any technical part of the experiment that could have suggested otherwise?
Yeah.
And my last question was.
Okay. Was there more to the question?
Yeah.
Okay. Should I just?
And at the end, I was like, yeah.
Okay. All right. Well, let me speak to that. I mean, I think that there are serious reasons, for skepticism about, the achievement of quantum supremacy, and there's also non-serious reasons, right? So let's start with the serious reasons. I mean, from the beginning, it's been clear that the biggest question mark about a quantum supremacy experiment like Google's is someone going to discover a much faster classical method to simulate this experiment, right? I mean, quantum supremacy is not like landing on the moon, that is like something that you just achieve for once and then it's for all time, right? Quantum supremacy is all about beating classical computers, right? And for that reason, because of that horse race aspect, it is something that could be achieved and then later unachieved, right? We could have quantum supremacy in 2020, and then we could lose it in 2021 when, if someone discovers, that there's a much faster classical way to simulate noisy random quantum circuits, or even, if they just, build much faster, much larger classical computers, then they could sort of temporarily remove the advantage of quantum computers. That second possibility I'm less worried about because as we all know, the advantage, as long as your classical algorithm is just doing a brute force simulation, is doing a sum over 2 to the n possibilities or whatever, then quantum computing is going to win, right? Like, this experiment used 53 qubits and, it can just barely be simulated using the largest supercomputers that currently exist on Earth, okay? Like Summit at Oak Ridge National Labs, which has 250 petabytes of hard disk space. Okay, now, if instead, so IBM estimated that Summit could simulate the Google device in about 2.5 days, as opposed to like 3 minutes to run the device itself. Notably, IBM never actually demonstrated that because it's not so easy to just get time on the world's largest supercomputer. I think it's very plausible that would work. Okay, but now suppose that Google repeats its experiment, but with 63 qubits instead of 53. Well, now you would need 1,000 summits, right? And so you're I mean it's true that classical computing is on a Moore's law trajectory, but quantum computing, it's very plausible that we could get up to 100 qubits, 150 qubits, and then you're way beyond what plausible advances in classical computing hardware are going to keep up with. In fact, ironically, the biggest worry you'd have at that point is that you could not even use a classical computer to verify the answer. Okay, so you'd have no way of checking your quantum computation. Okay, so as long as that's sort of the situation, that the classical computers are forced to resort to brute force to simulate this thing, then I would say that quantum supremacy is pretty secure. The real danger is that someone discovers, a much faster classical algorithm. And, there has been some exciting progress, even just within the past few months, on classical algorithms for spoofing quantum supremacy experiments. Now, none of this directly threatens the Google result, because the progress has mostly been for quantum circuits of a very small depth. Okay, so there was a recent paper by Aram Harrow and his collaborators, I think Rolando LaPlaca and others, that said, there's sort of a phase transition phenomenon. If you look at random quantum circuits on a two-dimensional grid, if they're a very low depth, then it will look, at least from the numerics, it looks like you can efficiently simulate that classically, approximately. But certainly, the Google experiment had a depth of about 20 for their hardest experiment. Aram tells me he thinks that they could only handle depth 3 or 4 before the phase transition would kick in. There was also work by Boaz Barak and his collaborators that says that you can spoof random quantum circuits, but with an advantage that decreases exponentially as a function of the depth. Okay, so you could spoof like a depth 20 quantum circuit. Maybe you could have a classical algorithm that would get a bias over random chance of a 1 in a million. Something. Now that was already that doesn't threaten the Google experiment, because they achieved a bias over random guessing that was like 1 in 500, right? That was already much better than that. So it's sort of enough to you think of this as like a modern version of the Bell inequality, right? Mm-hmm. Saying there's a classical value of that there's some score that you're trying to achieve with your samples in this quantum supremacy experiment, and you're trying to show that the quantum device achieves a higher score than any fast classical method could achieve, right? And so people are showing that, okay, classically you can get slightly better than the trivial value that you get from random guessing, but quantumly we've already gotten comfortably more than that. Mm-hmm. Okay, so but there could be a breakthrough in this subject, and that is the kind of thing that I think really would seriously threaten the achievement of quantum supremacy, and we should be completely clear about that it all depends on classical algorithms. I mean, with students, I have a couple of papers that give some theoretical evidence for the hardness of simulating these quantum supremacy experiments. Okay, so it says that if you can spoof Google's experiment, then you must have some kind of general ability to just simulate a random quantum circuit. That there's sort of nothing special about the particular statistical test that Google is doing. If you can spoof that test, then you can just simulate random quantum circuits better than chance. Okay, but maybe you can simulate random quantum circuits better than chance, and and that's the main fear that I have here. Now, I should say that even if a quantum supremacy is unachieved in that way, it could be reachieved, right? You then just have, they're like I think that we're now in the phase. It's kind of like Kasparov versus Deep Blue in chess, in the era between 1996 and 1998 or so, right? Where, there's a fight, for a little while, there might be a question in your mind, do humans or computers have supremacy at chess? After a while, it becomes no question, right? But we're now in the era where it's still, there could still be an exciting fight, and I think that my guess would be that a few years from now, that the quantum will have just completely decisively won it. But anyway, there are much less serious objections that people raised against the Google's experiment. Like they said, well, it doesn't count because it's not useful for anything. And to me, it's much more important to just show that a quantum computer can outperform a classical computer at something, than to do something that is useful, but where you don't give any evidence that you're actually beating a classical computer, right? Which is what a lot of the much hyped announcements in this field have boiled down to, right? So just first show the separation, and then we can look for what's useful from it, right? And and then there were more technical objections that were raised against the Google experiment by Gil Kalai, for example. I think it's fair to say that those objections have not survived. Google has just answered them. That some of them were just based on misunderstandings of the experiment.
Thank you for your answer.
Sure, no problem.
I think we can also tail a question by Louis Anderson.
Okay.
I can try to.
Sure.
So, Louis.
Hiya, can you hear me?
Yes.
Yeah, sure.
Awesome, great. So it's probably been somewhat mentioned before, but I was asking, what do you think are the sort of prospects of these variation algorithms going forwards? And have you seen recent results regarding sort of barren plateaus and what you think that might mean for the sort of field in general?
So unfortunately, you're asking me about things where I am not expert at all. I have not seen the things that you refer to. I mean, I'm familiar with variational algorithms, and unfortunately, I think that they belong in the broad class of things that we can try out. And we really, right now, we don't have a theoretical account that tells us what speed up to expect from it. I wish we did. They're in this huge class of heuristic quantum algorithms that you can try out. You can hope that you'll get a useful speed up. I wouldn't want to base the case for building a quantum computer on things like that, where you have no idea if you're going to see a useful speed up or not. But you might see one.
Yeah. Cheers. Great.
Sure. Yeah.
So another question, probably more tailored to the discussion of classical versus quantum. I think Matthias Leonardus has something about this. Matthias Leonardus.
Yes, that's you mean the question I asked in the Q&A thing?
I meant a question you asked, the field of theoretical computer science in general. But if you think that you have something more to join, yeah, go for it.
Okay, I don't actually remember that question because I sent it in the forum, but so you can read that one. I have one in the
okay, sorry. So in my opinion, your question was, where's the field of theoretical computer science moving and what is occupying the field's current attention? But I think after Scott has mentioned several results, I mean, you have mentioned that
I could address that question if you want me to.
Yeah.
It sounds interesting.
Okay, where is theoretical computer science moving? I mean, I think so and I mean meaning not only the quantum part of it, because theoretical computer science still has a classical component, as much as that surprises some of my friends in physics. But I think that it is moving on several fronts that maybe people in quantum computing might want to know about. One of them is for 25 years this field has tried to understand just what is the boundary between easy and hard problems, and especially for NP for NP hard problems, how well can they be approximated by efficient algorithms. And so the people are trying to close in on a full theory of that question, and this is related to this unique games conjecture that you may have heard of, which basically it's a conjecture that, if true, it would say that for a whole bunch of NP hard problems, that unless P equals NP, then the best approximation that you're going to get to the answer is in the worst case comes from a semi-definite programming algorithm, but by the way, people have tried to refute this conjecture by looking at quantum algorithms. This QAOA, the recent quantum algorithm that some people here may have heard of, started its life as an attempt to quantumly refute this unique games conjecture. Finding a fast quantum algorithm to solve these approximation problems. It didn't do that. Many people think that actually really these problems are all just NP hard, in which case we probably couldn't hope for quantum algorithms for them. My wife, Donna Moshkovitz, this is the main thing that she works on, just to take an example. There's lots of other interesting directions field. There's been some major recent progress on the minimum circuit size problem, which has been studied since the 1950s. Of given a truth table, like how hard is it to find the smallest Boolean circuit to compute that function? And there's a long-standing conjecture that this is also an NP-complete problem, but people haven't shown that yet. But they're making progress on it. There has been progress in the last decade on circuit complexity, which is sort of a code word for the attempt, the quest to prove that P is not equal to NP. Some of you may have heard of Ryan Williams. He had a breakthrough in 2011 when he showed that a separation was not P not equal to NP. You would have heard of that, but it was that a class sort of much larger than NP can put next non-deterministic exponential time cannot be simulated by another class that is much weaker than P. That was called ACC. Okay, and so this is a very far cry from proving P not equal to NP, but this was like the best progress that anyone had made in that direction for 20 years. Okay, and so building on that, there's been a lot more progress on circuit complexity, where like a lot of there are a lot of results that have like these really weird inversions, like if this, in order to prove that this problem is hard, you'd have to prove that this other problem is easy, but either this problem is hard or that problem is hard. There's a lot of sort of connections that have been discovered between all the different hard problems in circuit lower bounds and problems in de-randomization. So like taking randomized algorithms and making them deterministic. Problems in learning theory, can you even when these problems haven't been solved, they've been connected to one another in some very astounding ways. There's been lots of progress on the theory of error correcting codes, private information retrieval, and then classical algorithms. I would say one of the more exciting things that's happened in just classical algorithms in the last decade has been sparse linear algebra. So people know how to do linear algebra on sparse matrices super duper fast now, especially if you only need approximate answers, and they can use that to speed up lots and lots of fundamental algorithms problems, like maximum flow, for example. They can often get better solutions to discrete problems by finding continuous relaxations of those problems. There's a paradigm in algorithm design called the multiplicative weights update method that's been, just incredibly powerful. It actually came out of machine learning, and that's another obvious direction that in the last decade, deep learning has made these sort of astounding strides. Now, that has not been based on theory, right? That's just been based on taking the algorithms that we already knew about from the 1980s and scaling them up and just trying them on much bigger hardware with much more training data. And now, miraculously, it actually starts working. And now deep learning is actually went from what used to be called neural networks, went from kind of a novelty to sort of a major workhorse of the economy. And as I said, that has not been based on that has been much more empirical than theoretical. but a major push in theoretical computer science has been to understand what is going on. You know, can we theoretically understand when deep learning is going to work and when it's not going to work? So I hope that gives you a sense of some of the directions in theoretical computer science. What I said was very far from exhaustive, but if you went to the main conferences of theoretical computer science, Stock and Fox, they're called, and now of course they're being held virtually. Actually, now it should be easy to attend them. It's just like, I think the registration is like $50 or something, and then you can enter all of the Zoom calls. But if you went to the main conferences of theoretical computer science, those are some of the things that you would hear talked about.
Plenty of thanks.
Sure.
Maybe Mattis can also have his question later, but let's go through questions we have already.
Sure. Yeah.
So probably, I think I feel this is a question like to you as a Feynman of a computer science, because I'm pretty sure there shouldn't be a proper answer, but why do deep neural networks generalize so well in the over-parametrized regime?
That is so not the question. Rather, I am so not the person to try to answer that question. I mean, there's been a tremendous amount of work trying to answer that question, and the first thing, I would want to do is even familiarize myself with what has been done already on that question. But, but basically so that the question was about the over-parametrized regime. So maybe just to give the context for that question for people who don't know it, right? So like the theory of machine learning, as it was developed in the 1980s, say by Valiant and others, suggests that if you want generalization, if you want, to find a hypothesis that's going to actually do well at, or a model that's going to do well at predicting data that you haven't seen before, then you want that model to be much smaller than the data that you've seen, right? You want to have achieved a compression of your input data. Because otherwise you will always be vulnerable to overfitting, right? It's not impressive to fit, 5 data points using 6 parameters, because you could have fit anything, you could have fit them no matter what they were, right? And so then you have no guarantee that you're going to generalize, okay? But so that was a theory that was very well established, very well understood. I've taught it in my classes. And then deep learning came along, and people would train a neural network, that has, say, 1 million parameters, on only 1,000 points. And so, it is it has the potential for an absolutely massive amount of overfitting, and yet it would work, and this was just what they consistently found would happen, right? That even when you're in this over-parameterized regime where you have way more parameters that you could have fit anything, that nevertheless it works. So this is necessarily telling you something about the, not just about the model class, the neural nets, but about the algorithm that is being used to train the neural nets, right? So, if the neural net could have been trained in a completely arbitrary way, then you could have overfit. You could have fit any data at all, right? And the fact that you would fit this data would give you no guarantee that you could predict the next data, because you might have just stored all of the data that you saw in a gigantic lookup table, for example, right? And then you're like a student who's crammed for a test by memorizing a bunch of things, right? You've learned nothing except, for the things that you crammed, right? But in fact, the actual training algorithms that are used, the gradient descent methods, the back propagation, and so forth, don't work that way. And so you have to think about the model class and the training algorithm together. And one thing that people have done is they've said, well, it's true that these models are over parameterized, but often you can compress them, right? So you could feed them into a compression program, and you could find and you could find that if you look in that compressed representation, then actually you really have compressed the training data. And in that way, we sort of looking in from the outside can sort of explain how that neural net did as well as it did to predict the future data, even though the neural net itself didn't have to know any of that, right? But we, just by showing that we can compress it, we can show, we can explain how it could have been as successful as it was.
Okay, thank you. So we have one more question. We had like block of computer science by Stefan Moore. I'll try to allow him to talk if he wants to. But Stefan, can you say something to us? Or otherwise I wouldn't be able to ask his question because it wasn't like clear. Probably not right now.
Okay.
Okay. Okay. Then the question from Sam Coopers, if he also would be keen to ask it. Sam?
Okay.
Hello. Yes.
Hi.
I think my question was that computers are physical systems and different physical computers have different computational speeds. So how does computational complexity theory account for the different speeds of computers in classifying algorithms?
Yeah. So I mean, the short answer is that it doesn't need to, right? The entire point of theoretical computer science is to sort of study the contribution, to the difficulty of solving a problem that doesn't depend on the specific computer that you're using, right? That is only about the scaling.
I haven't seen these results about the parametrized.
Excuse me?
I think we.
Okay. That was So what you want to know is sort of what you have a hope of solving versus what could not be solved even within the lifetime of the universe, right? And I mean that is what the polynomial versus exponential dichotomy is trying to get at, right? But basically, if you know how many steps you need, let's say, within a given processor architecture, well then, making your computer twice as fast means that now you need half as much time, right? And that's completely obvious, right? But for the most part, the reason that theoretical computer science has not been so concerned with constant factors has been that there's never going to be a nice theory of constant factors because they're always going to depend on the hardware architecture, right? An algorithm that has a certain prefactor in one architecture might have a different prefactor in a different one, just depending on which instructions are available. And so this is one of the central things that you try to teach people. Like the very first thing to learn about theoretical computer science, is, are we interested in making computers 1,000 times faster, right? Sometimes people will ask me this, like, will a quantum computer be 1,000,000 times faster or 1,000,000,000 times faster, right? Because they're thinking about it as if it was a conventional computer chip, but just a certain number of times faster, right? What I have to explain to them is, no, the entire reason why this field is interesting in the first place is that there's not a numerical answer to that question, right? The entire reason that the field is interesting is that you're changing the whole scaling behavior of algorithms, right? You are making it so that you could do things in polynomial time that previously took exponential time, okay? And, it's true that, to know the asymptotic efficiency of a problem, right, that doesn't answer everything you'd want to know. And if you want to know how much speed up will I get for this real problem in practice, then you have to start, maybe you could start with the contribution of theoretical computer science, which is sort of what is the best family of algorithms, that we think exists or that has been discovered to exist for that class of problems. Next, you have to look at what is the best implementation of those algorithms that is out there. And then you have to look at what is the best hardware that I have available. How do I implement the best the best implementations? How do I adapt them to run the fastest on the hardware that I want them to run on, right? So there's all these issues that I have to worry about that are not issues of theoretical computer science. And I think, it would be wrong for theoretical computer science to sort of arrogate to itself that, oh no, those are our issues as well. No, those are not. Those are other people are the experts on those issues.
Great. Okay. Thanks very much.
Sure.
And I think like Matthias Leonardis has a question like probably related somehow to what we have already discussed. If he's keen to ask his question for like his second question.
Mm-hmm. All right.
Yes.
Yes. My question, okay, perhaps to explain it in two sentences. So when one thinks of kind of classical computations, people usually imagine like a programming language. And in this language, you would have sort of integers and strings, and you would manipulate them with arithmetic, and you'd have for loops and if loops and so on. Yeah. And so one issue with quantum computation is that it's sort of like one way to sort of say the question is like, what is the simplest thing you would have to augment this classical thing with, such that you would end up with a quantum computer? Is that known in any way? Because
I would say that it is. I mean, the simplest answer to that question is you want to augment it with an ability to apply quantum gates. Okay, so right. You need at some point you need the ability to manipulate qubits as qubits, put them in superposition states, do operations on the qubits that will entangle them. Okay, and so I think that the right way to think about programming a quantum computer, both in theory and also in practice, is think about programming a classical computer that gets to control a certain peripheral. Okay, where this peripheral is a device that can control qubits. Okay, so in other words, decide, I want to apply a Hadamard gate to this qubit, right? And that would just, in your favorite programming language, that could just be a function call that you'll make, a procedure that says, basically connect to this peripheral, aim this laser at this qubit, at this ion, in a way that will have the effect of applying a Hadamard gate to this qubit, okay? Or aim this laser in a way that will, apply a controlled NOT gate to this pair of qubits, okay? And, it was actually a super duper useful discovery that you could sort of separate out, all the parts of programming that deal with the conditionals, the loops, the control flow. All of that can be handled by the classical computer. Right, and the quantum computer can be used to do only the part that a quantum computer actually helps with, which is sort of the part in the middle, that does this big interference experiment, and then that sort of choreographs a pattern of interference, right? So if you look at how Shor's algorithm works, for example, the majority of the algorithm is classical computation, right? And you could just write code in your classical computer that would run all of Shor's algorithm, except for the part in the very middle that does prepares a superposition and then does a quantum Fourier transform, on it, and then measures. Okay, so I think that any classical programming language could be used. You just have to augment it with that facility to to manipulate qubits. And even from a theoretical standpoint, this turns out to be like the most convenient way to mathematically define what a quantum computer is. There was an earlier definition due to Bernstein and Vazirani that looked at quantum Turing machines. So just taking Turing's whole concept of a computer and quantizing it, that ends up being a complicated mess. It's much simpler to just think of a classical algorithm that then outputs a quantum circuit. So outputs, a description of what you'd like to do to some fixed collection of qubits. And I should also mention that there has been research on quantum programming languages, and even semantics of quantum programming languages, proofs of correctness of quantum programs. I don't know how much application this is all going to find. I mean, it might be that these inherently quantum programming languages will be useful. Maybe they're solving somewhat of the wrong problem. I don't think we're really going to know until we have the actual useful quantum computers and we have a whole community of developers who are using them to solve real problems. And then, in some sense, they're the ones who will tell us what are the programming tools that are most useful for that problem, right? It won't be decided by theoreticians a priori.
If I just a quick follow-up. So there isn't anything like, so for example, one could imagine just augmenting a classical computer with a factoring function, right? That wouldn't involve there being any qubits or anything like that. But I assume that if you just augment it with factoring, you cannot then efficiently simulate a universal quantum computer.
Right. We definitely don't think that. There is no indication whatsoever that factoring is a universal problem for quantum computing, right? Mm-hmm. If you had an oracle for factoring, how would you use that to simulate a quantum system, for example, to simulate a high temperature superconductor, right? It's like, one wouldn't know where to start. You could imagine a black box, the short answer to your question is imagine a black box that takes as input a quantum circuit and then tells you what that quantum circuit does. Or like samples from the output distribution of that quantum circuit. That is the black box that would encapsulate the power of quantum computing. And that's sort of a tautological answer to your question, but I think that's the true answer, right? Now, there are some interesting complete problems that people have discovered for quantum computing. So, problems that exactly capture the power of quantum computing, but not all of which are obviously about quantum mechanics. Now all of these are promise problems, which sort of means that they're not decision problems with yes or no answers, but many of them could be phrased as problems about estimating some quantity. Okay, maybe the most famous example of this is estimating the Jones polynomial of a knot, which is a certain invariant that you can compute for any knot. Any closed curve in three-dimensional space has associated to it a polynomial called a Jones polynomial, and it turns out that if you ask for what is the approximate value of that Jones polynomial at a certain complex number, like let's say the fifth root of unity, okay, then this is a complete problem for quantum computing. So any quantum computation can be phrased as estimating this Jones polynomial, and estimating the Jones polynomial can be done by a quantum computer. Okay, so if you had a magic box for estimating Jones polynomials, then that would completely capture the power of a quantum computer. Okay, now that might sound mysterious, but the real reason for it was a famous discovery of Ed Witten in the 1980s, which is that the Jones polynomial sort of secretly captures certain quantum field theories called topological quantum field theories, right? So that's what's going on under the hood there. Okay, so there are problems that capture the power of quantum computing in the way that you're asking for that are not on their face about quantum mechanics, but even those problems you might say are secretly about quantum mechanics.
All right, thanks. That's what I was looking for.
Yeah.
Okay, and so the next question will be from Joe Gibbs. I'm sorry, Scott. I just wanted to ask how much time do you have? Do you have any time
at some point I should get back to my kids, but if you want to do another 15 minutes, that's good.
Okay.
Would that be good? Or
yeah.
How much do you want? Okay. Sure.
Okay. If it's okay for you. Okay. From Joe Gibbs.
Sure.
Joe, you have to turn your mic on. Yeah.
Hi. In your theory space paper, about when you discuss quantum mechanics and sort of what would happen if it was any different, you talked about you discussed why the amplitudes need to be real valued because we need square root operations. But you didn't discuss anything about why they couldn't.
Sorry. Why they have to be complex? You mean?
Yes, you said they can't be real valued because we need square root operations.
Well, you can formulate quantum mechanics over the real numbers. It's a perfectly consistent theory. It's just that it's a theory that would lack, square roots of unitary operators that would live in the same dimension, right? So it would lack some of the nice properties that complex quantum mechanics has.
So the question I had was, okay, so if they can't be real valued, that's
well, I wouldn't say can't, but but there's some, okay, but go on.
But there's only understanding why they're not quaternionic, as opposed to.
I would say, okay, it's a good question. I would say that we actually have a much better understanding of why they can't be quaternionic than we do of why they can't be real. And the short answer is, I actually have a blog post about this that I wrote a couple years ago that you could look up if you're interested. But it basically explains in detail why, as soon as you have quaternionic amplitudes, then quantum mechanics goes completely haywire. Okay, and in particular, you get superluminal signaling. Okay, because quaternions don't commute, you can set up a situation where it actually matters, like whether Alice applies a unitary operation first and then Bob does, or whether Bob goes first and then Alice does, even if Alice and Bob are space-like separated. Okay, so even if they're in different galaxies, it can matter who goes first. Their operations don't commute. If operations don't commute, that means that one of them can send a signal to the other one. Okay, and so now you get faster than light communication. Okay, that's the simplest way of understanding what goes wrong if amplitudes could be quaternion. And that is not nearly as well known as it should be. In fact, part of the reason I wrote that blog post was to say, like wait a minute, this is just trivially true, right? Well, why don't people real? So people did realize that, right? There's a whole book about quantum mechanics over the quaternions by Steve Adler, and like I knew that this book existed, and I was like, why is this a whole field that people study if it just you just immediately get nonsense, you immediately get superluminal signaling. So then what happened was that Steve Adler, who's is still around, and he was kind enough to actually post on my blog, and and came and talked to us, and the answer is that he had a way of sort of trying to make the superluminal signals fall off exponentially with distance. Okay, so there would still be superluminal signaling in his version of quaternionic quantum mechanics, but it would be very, very hard to notice, at any reasonable separation. Okay, but then he sort of, even that version of quaternionic quantum mechanics he abandoned for other reasons, because it didn't solve the problems in particle physics that he thought that it could solve, basically. But but I think that it's good for everyone to know that once you make amplitudes into quaternions, then you don't have commutation of space-like separated operators, right? Which means now you've got to at least worry about superluminal signaling. You also have, just tensor products just no longer work the way that you hoped that they would work, right? So it's if you try to form a space of density operators by taking the tensor product of smaller spaces of density operators, you will not get the global space of density operators on the larger space, right? It's just so a lot of things will break that you just took for granted in standard quantum mechanics. Much more so, by the way, than in real quantum mechanics. Real quantum mechanics work, almost entirely works fine, except for this, square root issue, and a few things that are maybe less elegant, less nice, having to do with counting the number of parameters in a mixed state and things like that. But despite being less elegant, I would say at least it's sensible. Whereas quaternionic quantum mechanics, I would say, is not even really sensible. All of these things, real quantum mechanics, complex quantum mechanics, quaternionic quantum mechanics, they actually all lead to the same power of quantum computation. Okay, so you can define quantum polynomial time in all three of these theories, and you can show that you get the same power for all of them. Okay, but if you try to ask so quantum computation is one of the most insensitive things to, the specific, variant of quantum mechanics that you're working under, okay? But if you try to ask more detailed questions, like, can Alice and Bob, send signals faster than light? Well, then, that breaks in quaternionic quantum mechanics. Now, if you try to ask an even more detailed question, like, is the number of parameters needed to specify a density matrix, does it multiply across subsystems in the way that I would hope that it would, then that breaks even in real quantum mechanics, okay? And complex quantum mechanics is like a sweet spot where you get, not only like mathematical consistency, you get all the nice properties that you would have liked. Maybe that's why God favored the complex numbers. I don't know.
Oh, that's great. Thanks for the answer.
Sure. No problem.
Okay, the next question probably, I know John Preskill tells a lot about this, but maybe just a short answer from you. Will quantum computing give any insights for quantum gravity? And if so, how?
Yeah, well, I think that the field of quantum computing, quantum information, is already giving a lot of insights about quantum gravity, or at least that is what the quantum gravity people believe, what many of them now believe. So there's this entire direction of it from qubit, that was started by Lenny Susskind and a bunch of his collaborators. Preskill has been very involved in it. Daniel Harlow, Patrick Hayden, Brian Swingle, Juan Maldacena. So there's been this whole direction of using ideas from quantum information, ideas of qubits, quantum circuits, entanglement, even complexity. Complexity of quantum states to analyze quantum gravity, especially in the context of this ADS-CFT correspondence, right? Because the whole virtue of, so the ADS-CFT correspondence is maybe, considered the most important thing to have come out of string theory, maybe, right? And, it's a duality between a quantum gravity theory in, not quite in our universe, but in an anti-de Sitter universe, and an ordinary quantum field theory, a conformal field theory, CFT, with no gravity that lives on the boundary of the anti-de Sitter space. And, these are theories that look completely different, involve different numbers of spatial dimensions even, but they're related by some kind of duality. And in the last 5 or 6 years, people have reinterpreted that duality as literally an example of a quantum error correcting code, okay? Not just analogous to a quantum error correcting code, it literally is one, okay? The mapping from the bulk states to the boundary states is what's called a holographic mapping. If you've heard of this holographic principle as one of the central ideas of quantum gravity, that, the physics inside of a region should be sort of somehow encodable on the boundary of that region, right? So that's precisely what happens in ADS-CFT. But, it was understood from early on that the mapping cannot be a local one, okay? So if I have just one tiny little, particle wiggling around somewhere in the bulk, then to model that, I might have to change, a whole enormous number of qubits that live on the boundary, okay? But, and then people said, well, that's kind of analogous to what happens in an error correcting code, right? That I encode a single physical qubit using a large number of logical qubits. And it turned out that connection went extremely deep. And so you can view ADS-CFT as precisely an example of an error correcting code, a quantum error correcting code, one that involves tensor networks, okay? And then people have, used the idea of quantum complexity, right? If you try to identify some quantity on the boundary theory, so in the conformal field theory, that is sort of tracking what is happening to the geometry of the anti-de Sitter space. So for example, if you make a wormhole between two different regions of space, and then, general relativity will just stretch that wormhole out, just, have it grow with time. And then Susskind famously asked the question about 7 years ago, well, what quantity on the boundary is sort of tracking? What quantity could we point to in the boundary theory that knows about the length of this wormhole, that knows how it's growing with time? And he said the only reasonable candidate that he could think of was the complexity of the quantum state, meaning just how many gates would you need to create that quantum state in a minimum circuit for it. Now, I'm skeptical myself that circuit complexity could possibly play such a fundamental role in the laws of physics as Lenny is positing for it, right? Ironically, I'm sort of the skeptic about, compared to Lenny, about the role of complexity in physics. But I think that he's absolutely right that no one has been able to come up with a better CFT quantity than that. And so at any rate, the tools of, the language of circuit complexity is now sort of the language that at least this part of the quantum gravity community is using, right now to sort of talk about quantum gravity. And, there was this firewall paradox. So like the most modern refinement of Stephen Hawking's black hole information problem was called the firewall paradox from 2012. And I think one of the leading resolutions to that by Daniel Harlow and Patrick Hayden was, essentially relied on the idea of complexity, of saying that sort of the event horizons of black holes are somehow shielded by certain problems being exponentially hard, or even for quantum computers, right? If those problems were easy to solve with quantum computers, then you could sort of imagine doing an experiment where you would sort of destroy space-time at the event horizon of a black hole. Where if you jumped into the black hole, you would see a firewall, which means, an end of space-time, because you're supposed to see an end of space-time at a black hole, but you're only supposed to see it at the singularity, right? This would be an end of space-time that would happen already at the, they would prevent you from crossing the event horizon. Okay, but, it's believed that is very, very hard to cause to happen. And the reason why it's so hard is really a reason of computational complexity, okay? So there are these really striking connections that have been made. There was a paper just this year by Boland, Pfefferman, and Vazirani that says that quantum gravity might give you a counterexample to what's called the quantum extended Church-Turing thesis. So you might be able to use quantum gravity to do something beyond what even a quantum computer would let you do in polynomial time. Unfortunately, there's no one person who gets to see the result of the computation, right? And there's a couple reasons for that. First of all, if you want to see the answer to their computation, the one that's too hard even for a quantum computer, you have to jump into a wormhole and you can never get out of it again, okay? So you have to really want the answer to this question, okay? You can't tell, you can never communicate the answer to anyone outside of the wormhole, okay? But it's worse than that, because no one person who jumps into the wormhole will ever learn the answer. Just if you combine the experiences of a bunch of people who all jumped into the wormhole, who jumped into it from different ends, then combining all of their experiences, you could extract the answer from that, okay? And I should also say that this is a problem that is inherently a quantum problem. It involves measuring quantum states to see whether they're sort of random or pseudo-random. And, but it's a problem that information theoretically, it could be solved, but we just think that with a standard quantum computer, you would need exponential time to solve it. But if you had this ability to combine the experiences of all these observers who jumped into wormholes, then you could learn an answer in polynomial time, at least within this ADS-CFT context, in this anti-de Sitter universe that is not quite the universe that we live in, okay? Okay. So I mean, I'm giving you some examples of how I think that ideas of quantum computing have totally transformed the study of quantum gravity over the last decade. And that's been one of the most exciting things to come out of quantum computing, to be honest. Now would, building an actual physical quantum computer, would that also help? Well, it might. I mean, that would mean that you could actually simulate some of these quantum gravity models, and then you could as long as you could formulate your question in the right way, you could run simulations of quantum gravity models on a quantum computer. In fact, that might even be doable in the NISQ era. That might even be one of the earlier applications of a quantum computer that is technologically feasible to do. Now, will you learn anything from these experiments that actually tells you something new about quantum gravity? That's a much harder question that I'm not sure about the answer to.
Okay, thank you. Well, I think we have run out of our 15 minutes, which you gave.
Well, okay. I mean, are there more questions? I mean, if
there are,
how many more?
I think maybe 3.
Something. All right, I'll tell you what. If it's just 3 questions, then let's just do those 3 questions, and then and then let's call it a day. How about that?
Okay, so thank you very much. So the first question was probably more related to the beginning of our talk. Will the first applications of quantum computing be for quantum chemistry? And if so, why aren't more theorists working on that?
Oh, well, so the short answer is these days a lot of theorists are working on that. I mean, or rather, I would say that they're working on the more general problem of quantum simulation, right? So you have so there's been a lot of theoretical progress over the last decade on the problem of Hamiltonian simulation, right? Where a Hamiltonian is specified to you in some way, and you would there are obvious ways that you could simulate it on a quantum computer, like what's called trotterizing your Hamiltonian, just slicing it up into a bunch of discrete pieces and then doing them one by one. But those incur a lot of overhead, and you would like to remove that overhead. And there's been a lot of progress in that direction, especially involving a new idea that's called LCUs, linear combinations of unitaries. Okay, and you can look at just Google for the papers about that. I think Robin Kothari at Microsoft has done a lot on this. Andrew Childs and a bunch of others have been working on that. And they were able to take algorithms, where a decade ago, all that was known was that if you wanted to solve this quantum chemistry problem on your quantum computer, you can do it in polynomial time. But the polynomial might have been, n to the 10, n to the 12, something completely impractical, right? But then what happened over the last decade is that the n to the 12 became an, n to the 6, became an n to the 4, became an n to the 3. And now a lot of these things are nearly linear time. Okay. Now, unfortunately, that still doesn't mean that we can do it in practice in the NISQ era, right? A lot of it is still very limited by depth, and you could say, okay, we now know that it would be enough, if you want to learn something new about chemistry, like 100 or 200 qubits should already be enough for that, which was not obvious when people started, okay? But they still have to be 100 or 200 really good qubits. So let's say able to support, 1 million layers of gates, like a depth 1 million circuit. And right now we think, we can do a depth 20 or a depth 30 circuit, right? So there's still a large gap between where the technology is and, and what the algorithms really want. But, I think that people are going to continue hammering away at these problems. Unfortunately, once it gets down to sort of, just can you fit it into a NISQ quantum computer, then it becomes a very, very, like the closer you get, you could say, to doing it in real life, the less clean the questions become, right? The messier and more detailed it becomes, and it becomes less and less a question of general principles and more a question of just trying to get a win for this, whatever particular application you had in mind. But I think that, it is worth getting that win, right? People really should think through the full stack, and, they should, I think that there's definitely room for more theoretical progress on, improving the depth, especially of these quantum simulations. And, also, by the way, there are much more general questions that would feed into this. Like, can you do useful quantum error correction with a much lower overhead than how we know how to do it currently, right? And if you could figure out how to do that, then that would make, quantum chemistry simulations in the NISQ era, like, enormously, closer to reality, for example. So yeah, but I think that it's going to be a collaboration between, theorists and experimentalists and everyone in between.
Okay, thank you very much. So I think the next question is kind of Oxfordish, let me say so. So
it's sort of what?
It's sort of Oxfordish, like
Oxfordish.
Yeah, I mean, like, what is your take on many worlds interpretation?
Yeah.
And if interpretation does really matters for quantum computing?
Yeah. Well, okay. So the answer to the second question is that every interpretation makes the same predictions for what any quantum computation is going to do when you run it, right? And in fact, this is why they're called interpretations in the first place. This is why they're not called, rival physical theories, right? The only view of quantum mechanics that would sort of disagree about what a quantum computer is going to do or what it's going to be good for would be, a view that would say that quantum mechanics is not exactly true, right? That quantum coherence cannot be extended to arbitrary scales, that there's going to be some dynamical collapse of the wave function, or some limit of complexity of the quantum states that could exist in our universe, right? But if you believe, if you believe any of that, then the issue is not one of interpretation, right? The issue is that you have a rival theory to quantum mechanics, right? That makes a different empirical prediction, and it would be absolutely wonderful if the attempt to build a quantum computer can test some of those predictions. I mean, as I said at the very beginning of this Q&A, right? That's sort of, in some sense, that's the main reason why I got interested in quantum computing in the first place, just to test quantum mechanics at this, to prove that it works at this kind of scale. Okay, but now, regarding the interpretations, I mean, the way that I like to think about it is, there's a very, very simple decision tree, right? I mean, the first question is just, do we agree that quantum mechanics is exactly true? That it's a framework that applies perfectly to everything in the universe, right? Because it might not be, but if so, that that is an empirical matter, right? If it does perfectly describe all the experiments that we could ever do, then there's a question of sort of what is the point of physics? What's the goal of physics at all? And there are people who take a very, very subjectivist view of that. They say, I don't even want to talk about what is the state of the universe. I think that's too metaphysical, right? I just want to talk about my experiences or the experiences of observers. And there's a huge danger that you'll go into solipsism that way, right? And you'll say, oh, I exist, everyone else might have a quantum state, but I'm just an observer, right, who's external to, to the Hilbert space, which seems kind of silly, and they have complicated ways of talking around that. But that's what Bohr and Heisenberg would have wanted to do, right? And I like to say that, to me, the Copenhagen interpretation simply means shut up and calculate, except minus the part where you shut up. Okay, so. It's just a whole philosophy that says, we just have to talk about the experience of observers. We don't have to talk about the state of the universe. Okay, but now the alternative to that is to say, no, there is a real state of the universe. It was here before we were here. It was here at the Big Bang. We're just some, little, sort of pond scum or, some patterns that happen to arise on that state. on the surface of one planet orbiting, one star. And, we're, as much a part of the state of the universe as are the atoms that we're measuring, and quantum mechanics has to apply equally to all of it. If you believe that, then I think the next question is, well, now, do you get, without changing quantum mechanics, do you get to add anything extra to it to say that a measurement has a definite outcome? Okay, if you want to add something extra, then you could, for example, take a hidden variable theory, such as most famously the de Broglie-Bohm theory, right? Bohmian mechanics, right? That says, yes, there is this whole superposition, but there's also, there's sort of a definite thing that happens, which is sort of guided by the superposition in a way that will exactly reproduce the predictions of quantum mechanics. And, and then you have sort of an embarrassment of riches, because there are many different such theories. And it seems like empirically, you could never decide which one was true, right? There's also, these theories don't play so nicely with relativity. They require you to choose a preferred frame of reference, which wouldn't have empirical consequences, but it might be unsettling to us. So then, the alternative to that is if you say, no, I think that there is a real state of the universe, it's precisely governed by quantum mechanics, and we don't get to add any extra mathematical ingredient to quantum mechanics. At that point, I would say that you are a many-worlder, okay? At that point, you believe the same thing that Everett said in 1957. And, there's a lot of people who want to go down that branch of the tree, but who will then want to say, no, but I don't literally believe in many worlds, and, invent all kinds of fancy sounding ways to talk around it. But as far as I'm concerned, at that point, you do believe in many worlds. You believe that there is a quantum state of the universe, and it has a whole bunch of branches, and, we're just one of the branches, but there's no reason to say that the other branches would not, have experiences, in the same way that we do. So in some sense, like, I've sort of answered your question like a comparative religion scholar or something, right? I've said, this is the, brand, I will go to the mat for the position that this, if you want to go down that branch of the decision tree, then you are led to many worlds, right? And so, in some ways, it is sort of the simplest interpretation of quantum mechanics. It is the least extravagant one, except it's the least extravagant mathematically, you might say, even if it's the most extravagant in some metaphysical way, okay? And, but now to actually answer the question of, assuming that there is this quantum state of the whole universe, are the other worlds are they zombie worlds? Is there anything that it's like to be in those worlds? Are they just sort of ghost towns? Or, do they have conscious experience, just like we do? I mean, I think that, this starts feeding into some of the most ancient questions that no one has been able to answer, questions about what is consciousness, right? What causes it to exist? It's not clear how much progress humans have made on these questions, even after thousands of years. But I think that one can at least clarify the branches of the decision tree. One can say that many worlds is in some ways is the most conservative interpretation, right? It's the one that sort of adds the least to just the bare picture of quantum mechanics. But then what it leaves is for us to figure out how to derive, how to recover our experience, from that, which admittedly would be a problem for any interpretation, right? But maybe it's especially a problem, if you think that all of these worlds are equally real, and then you have to explain not only, our experience of one of them, but our experience of each world with precisely the probability that, would be predicted from the Born rule.
But what is your personal preference?
I just told you. I mean, no, I mean, I try not to, think based on gut feelings. I mean, I have a lot of personal liking for the sort of this sort of cosmological view that's due to Busso and Susskind, which basically says that, you know, sure, you could believe many worlds if you want, but the issue is that once you've made a decision, let's say, and once the sort of news of that decision is has gotten entangled with some, or gotten encoded into some photons that are that have now leaked into space and that are flying away from the Earth at the speed of light. Well, now, you know, we could never again catch those photons in principle, even if we wanted to, right? So at that point, like, we might as well agree with the Copenhagenists that, you know, the wave function has collapsed, or that, you know, the sort of decoherence has happened in a completely irreversible way now. Right now, you know, recoherence can never again happen, even in principle. Okay. Now, you know, the issue is that this is a bit of a teleological criterion, because this, you know, if aliens had thought to sort of surround the Earth with perfectly reflecting mirrors, right, then, you know, okay, then maybe you could recohere the state. But, you know, we're relying on the fact that they haven't done that. And then, you know, it seems unlikely that any aliens are going to, you know, surround our solar system with mirrors or something like that. You know, and so then, you know, the criterion for the wave function to have collapsed would then be, you know, are the records of this quantum event traveling toward the de Sitter horizon of our universe, right? And by the way, just to come back to an earlier question, now it would actually matter that we are living in a de Sitter universe and not in an anti-de Sitter one. Okay, now it actually matters that we're not in this ADS-CFT, you know, toy universe, right, where there is a boundary, you know, that can make things completely unitary. Okay, so maybe it matters that, you know, maybe the problem of interpreting quantum mechanics is solvable in a de Sitter universe in a way that it is not solvable in an anti-de Sitter universe. Okay, is what I'm saying. Okay, and then, you know, you could sort of reconcile the many worlds in Copenhagen views and say, you know, they're both right in a way. They were just sort of talking about it differently. So I have some sympathy for that. But, you know, I really hope that we learn more. My real hope is that some new discovery gets made, whether it's an empirical discovery, you know, that either changes quantum mechanics or something new on top of quantum mechanics, something new from cosmology, or, you know, some new mathematical discovery about quantum mechanics that just forces all of the interpretations to reshuffle their cards. Okay, you know, that changes the whole debate. I think that's the thing that I would most like. So, you know, like an analogy would be like Gödel's incompleteness theorem. Like, it didn't settle, you know, it didn't settle all debates about the foundations of math, right? But it made every camp in the foundations of math, you know, they might have continued believing the same things, but suddenly it was for a different reason than before. Okay.
So thank you very much. I think we have answered like most. If you have something left, sorry, we had already like spent a lot of time.
Yeah, no. So look, thanks for doing this. It was a lot of fun, and thank you for listening.
Thank you. We'll hope like the United States won't collapse in 6 months, and like that.
I hope so as well. Actually.
Yeah, and that coronavirus will end soon, and you'll be able to.
Yeah, it would be fun to be able to travel again. Yeah. So, all right. Well, yeah. So thanks again for inviting me.
Thank you very much. Thank you everybody who attended us, and take care of yourself. And if you want to come us next week, thank you very much.
Great. So bye.
Goodbye.